If you stop and look around, I mean, really look at the stuff that makes up our world, you're basically sitting inside this giant, elegant chemical puzzle. Like, why is the body of your car this solid, shiny, rigid piece of metal, but then the tiny little connectors inside its computer, its circuit board, they're wrapped in this dull, kind of flexible plastic?
Yeah, or think about cookware. Why use these heavy, thick materials, but then you have to worry about them rusting away?
Exactly.
It all comes down to this fundamental split in the universe of elements, metals and nonmetals. And this isn't just, a neat table in a chemistry textbook. It's
Yeah.
really a story. It's about their inherent physical traits, their personalities, if you like, and sometimes these spectacular chemical fights they get into.
So today we're diving deep into the sources we've gathered on these absolute building blocks of everything. And our mission isn't just to list definitions. We want to get into the real insights.
Right, the weird exceptions, the rules of how atoms are actually built.
And how all these characteristics basically dictate everything we engineer.
Yeah.
From a tiny piece of jewelry all the way to something ancient and mysterious like the Iron Pillar of Delhi.
So let's start with the basics then. If you just glanced at an element, what two properties would immediately make you think, okay, that's probably a metal?
Shine, definitely.
Yeah.
And that metallic glint.
Yeah.
And probably hardness. Metals are supposed to be reflective, shiny, and, tough. That feels like the main rule.
That is generally the rule, yeah. But the sources we looked at, they immediately start pulling the rug out from under that idea. We assume luster, that classic metallic shine, is just for metals.
But I think I remember reading about a non-metal that kind of breaks that rule.
Exactly. You're thinking of iodine. It's a non-metal, but in its solid form, it has this really distinct, quite beautiful metallic luster.
A shiny non-metal. Okay, so first assumption, already a bit shaky.
Right. And then there's hardness. You think metal, you think tough, unyielding.
Yeah.
But then you meet the alkali metals family, lithium, sodium, potassium. I mean, they're metals, technically.
But they're famously soft, aren't they? Like, you can cut them with a regular knife.
You can. They're incredibly soft, surprisingly light, and they have really low melting points, too. They just completely defy that typical heavy, high melting point metal image.
And the contrast works the other way, too, right? Like with carbon?
Precisely. Carbon's a nonmetal, but one of its forms, one of its allotropes, is diamond.
Which is famously the hardest natural thing we know.
The hardest. With melting and boiling points that are just astronomical, it shows the physical spectrum is way broader than just hard metals and soft nonmetals.
It's fascinating how these properties then directly lead to how we use them. Think about malleability and ductility.
Right, the workability.
Malleability being able to hammer something into thin sheets, and ductility pulling it into thin wires. Nonmetals usually just shatter if you try that.
But metals, you can shape them, stretch them.
And the champion, the absolute king of stretchiness, has to be called.
Oh, absolutely. The sources had this incredible fact about its ductility. Get this. You take just 1 gram of gold. Tiny amount.
Okay. You can draw that single gram into a wire that's about 2 kilometers long.
2 kilometers from 1 gram. That's unbelievable.
It really is. And that incredible workability, that's why metals are so central to technology. We can manipulate them into almost any shape we need.
Okay, let's switch gears slightly. What about conducting heat and electricity? That's a big one for metals.
Huge. Metals are generally excellent conductors of both. Silver and copper are like the best for heat.
Though some aren't great, right? Like lead and mercury?
True, they're relatively poor conductors compared to copper or silver, but the general rule holds. Metals conduct well.
Which brings us back to that wire puzzle at the start.
Exactly. The wire itself is metal because it needs to carry the electricity efficiently, but it has to be coated.
With plastic or rubber, which are nonmetals.
Right, because they are insulators, they don't conduct electricity. That coating is the safety barrier preventing the electricity from finding an easier path, like through you if you touched it. Okay, we mentioned melting points before, usually high for metals, but what about those weird ones, gallium and cesium?
The melting paradox. Yeah, gallium and cesium are metals, but they are so incredibly sensitive to temperature.
How sensitive?
So sensitive that if you just held a piece of either one in the palm of your hand,
Your body heat would melt it.
your body heat alone is enough. They literally melt in your hand. Solid to liquid just like that around room temperature.
Wow. Okay, and one last physical thing, something we actually hear, the idea of being sonorous.
Yes. Sonorous.
Yeah.
It just means they make a distinct ringing sound when you strike them.
Which is obviously why bells are made of metal.
Every single one, from tiny handbells to huge church bells. If you hit a non-metal block, you just get a dull thud. So it's this combination of hardness, conductivity, workability, sonorousness that really defines the usefulness of metals as a class.
Okay, so we've covered the physical side, the look and feel. But now let's dive into the chemical side, the reactivity. This is where things seem to get, well, dramatic. What's the fundamental chemical move for a metal?
The basic rule, generally speaking, is that almost all metals will combine with oxygen to form metal oxides.
Oh,
And crucially, these oxides tend to be basic in nature. Think about burning a magnesium ribbon. You get that incredibly bright, dazzling white flame.
yeah, I remember doing that in school.
And what's left is magnesium oxide, a basic compound.
But chemistry's never that straightforward, is it?
Yeah,
There are always exceptions, like these amphoteric oxides.
exactly. They're like the chemical diplomats, as you put it earlier.
Uh-huh. I like that.
Elements like aluminium and zinc, their oxides are fascinating. They can't quite decide if they want to be acidic or basic.
So they react with both.
They react with both acids and bases, producing salt and water in either case. They kind of adapt their chemical personality depending on what they're mixed with. Very flexible.
Okay, so you have the flexible ones,
Yeah.
and then you have the chemical drama kings, like sodium and potassium.
Oh, absolutely. Their chemical personalities are just incredibly volatile. They react so violently, so vigorously with oxygen.
That they just catch fire
Yeah.
on their own.
Spontaneously. If you just leave them exposed to the air, they'll burst into flame. It's an incredibly energetic reaction.
Which explains the storage secret, right? Why they have to be kept under oil.
Precisely. They have to be kept submerged in kerosene oil. The kerosene acts as a barrier, a seal, preventing any contact with oxygen or moisture in the air. It's purely to stop them from instantly combusting.
Wild. And their reaction with water is just as intense, isn't it? It sort of depends on the metal.
Very much depends. If you take sodium or potassium and drop them into cold water, the reaction isn't just fast, it's explosively exothermic.
Meaning it releases a ton of heat.
So much heat that the hydrogen gas produced by the reaction immediately catches fire.
So you literally get fire on water.
We get fire on water. It's quite spectacular and dangerous. Now, compare that to metals like calcium or magnesium. They react, but much less violently.
Right.
And here's a really cool visual detail from the sources. When calcium and magnesium react with water, magnesium needs hot water, calcium does it in cold, they start to float.
Float. Why do they float?
It happens because the bubbles of hydrogen gas that are produced stick to the surface of the metal. These bubbles act like tiny life preservers, lifting the metal up to the surface.
Huh. A chemical life raft. That's neat.
Isn't it? Then you get the even pickier metals, aluminium, iron, zinc. They don't care about cold water or even hot water. They'll only react with high temperature steam.
And then they're the ones that just don't react with water at all.
Right. The completely indifferent ones at the bottom of the reactivity scale, lead, copper, silver, gold, they just ignore water entirely. No reaction.
Okay, the drama continues with acids, I assume.
Oh, yes. Generally, metals react with dilute acids to produce a metal salt and hydrogen gas. Magnesium, being pretty reactive, usually does this quite vigorously. You see lots of bubbling.
But there's a big catch, isn't there? Something about nitric acid, text HNO93K.
Ah, nitric acid. Yes.
Yeah.
This is where the acid really shows its muscle. Usually, when a metal reacts with nitric acid, you do not get hydrogen gas bubbling off.
Why not? What happens to it?
Because nitric acid is a really powerful oxidizing agent. It's like an electron bully.
Okay.
As soon as any hydrogen gas, H2 tries to form, the nitric acid molecule swoops in, rips electrons away from it, and oxidizes the hydrogen into plain old water. It happens so fast the hydrogen never escapes as gas.
Wow. It stops the expected reaction cold.
Pretty much. The only way around it, the sources say, is if you use a fairly reactive metal like magnesium or manganese and react it with very dilute nitric acid. Then the acid is just weak enough that some hydrogen might manage to escape before being oxidized.
It's a chemical battle of strength.
It really is. And speaking of chemical power, we have to mention the ultimate chemical weapon, in a sense, aqua regia.
Royal water in Latin, right?
That's the one. It's this incredibly corrosive mixture. You make it by mixing concentrated hydrochloric acid and concentrated nitric acid, specifically in a 3-to-1 ratio.
And what makes it so royal?
It's one of the very few things in existence that can actually dissolve the so-called noble metals gold and platinum. Neither concentrated HCl nor concentrated HNO33 rollers can do it on their own.
But together.
Together, in that specific ratio, they can dissolve gold. It takes this powerful tag team to conquer the most chemically resistant metals.
Okay, so we've seen metals catching fire, floating on water, fighting off acids. All this chemical action implies there must be some kind of ranking, right? A hierarchy.
Absolutely. All this chemical fighting leads directly to what chemists call the reactivity series, or activity series. It's basically the definitive scoreboard.
The chemical pecking order.
Exactly. It arranges metals in a strict order, from the most reactive at the top, like potassium and sodium, the ones that explode in water, all the way down to the least reactive at the bottom, silver and gold, which, as we said, do almost nothing.
And this series isn't just for show. It's incredibly useful because it lets you predict what will happen in certain reactions, like displacement reactions.
Precisely. If you have metal A and it's higher up on the reactivity series than metal B.
Meaning metal A is more reactive.
Right. Then metal A will actually kick metal B out of its compound. If you put metal A into a solution containing a salt of metal B, you'll end up with the salt of metal A, and metal B will be pushed out as the plain metal.
The stronger, more reactive metal always wins the spot in the compound.
Always. Metal A plus salt of B becomes salt of A plus metal B. The series tells you who wins.
But why? Why does this happen? What's driving all this reactivity, this electron swapping?
To understand the why, we need to zoom right down to the level of atoms and their electrons. The fundamental driving force behind almost all chemical reactions is the quest for stability.
Stability.
Specifically, achieving a full, stable outer shell of electrons. Atoms want to have that complete outer layer, like the noble gases have. It's the most stable arrangement.
Okay, and metals are usually on the left side of the periodic table.
Which means they typically have just 1 or 2 or maybe 3 electrons in their outermost shell.
So it's easier for them to just get rid of those few extra electrons.
Exactly. It takes less energy to lose those few outer electrons than to try and gain enough to fill the shell. So metals tend to lose electrons.
And when they lose negatively charged electrons, they become positively charged ions, right? Cations?
Correct. Like sodium loses 1 electron to become a sodium ion, texane A plus $. Magnesium, Mg, loses 2 to become texane A plus $. They become positive tations.
And nonmetals are the opposite. They're on the right side of the table.
Meaning they're close to having a full outer shell already. They might just need 1 or 2 more electrons.
So it's easier for them to gain electrons.
Much easier. They gain electrons to achieve that stable configuration. And when they gain negative electrons, they become negatively charged ions called anions. Like chlorine, Cl, gains 1 electron to become chloride. Oxygen gains 2 to become oxide, Tex2O.
So picture sodium metal meeting chlorine gas. What happens at the atomic level?
Sodium, the metal, happily gives away its single outer electron. Chlorine, the nonmetal, eagerly accepts that electron to complete its outer shell.
So sodium becomes texture plus chlorine becomes texture.
And now you have these 2 ions with opposite charges, positive sodium, negative chloride, and opposites attract.
Strongly.
Very strongly. They're pulled together by powerful electrostatic forces. This electron transfer creates what we call an ionic bond.
And that forms an ionic compound like sodium chloride table salt.
Exactly. Or magnesium chloride, text MeCl2, where 1 magnesium atom gives away 2 electrons, 1 to each of 2 chlorine atoms. You end up with text Nus 11 and 2 text Charles, all held together tightly.
And the strength of these ionic bonds, this powerful attraction, explains their physical properties too, doesn't it?
Absolutely. It explains why ionic compounds like salt or calcium oxide have such incredibly high melting and boiling points.
The sources mentioned the numbers Tex-Nest Tero melts at over 1,000 Kelvin. Tex-Tero at over 2,800 Kelvin.
That's right. You need a huge amount of energy, a huge amount of heat to overcome those strong electrostatic forces and break the ions apart, allowing them to move freely as a liquid.
Ah, and that moving freely part is key for conducting electricity too, isn't it?
Crucial. In their solid crystalline state, the ions are locked rigidly in place. They can't move.
So solid salt doesn't conduct electricity.
Correct. But if you melt it, or if you dissolve it in water, the ions are now free to move around.
And because they are charged particles, ions, their movement constitutes an electrical current.
Exactly. So ionic compounds only conduct electricity when molten or dissolved in solution, because that's when the ions are mobile. The freedom of movement is everything for conduction.
Okay, so this reactivity series, this chemical scoreboard, it doesn't just predict simple reactions in a beaker. It actually dictates how we get metals out of the ground in the first place, the whole field of metallurgy.
Absolutely. A metal's position on that series tells engineers exactly what kind of industrial process they need to use to extract it from its ore.
So for the really reactive ones at the top, potassium, sodium, aluminium,
Yeah.
They're clinging tightly to whatever they're bonded with, usually oxygen.
They hold on to those bonds fiercely. You can't just use simple heat or even a reducing agent like carbon to persuade them to let go of the oxygen. Their chemical desire to stay bonded is too strong.
So we need something more drastic. The sources call it electrolytic reduction. Sounds intense.
It is intense and incredibly energy hungry. Because these metals want to stay combined so badly, we literally have to force them apart using electricity.
How does that work, basically?
You have to take the metal compound, usually the oxide or chloride, melt it down at very high temperatures, and then pass a massive electrical current through the molten liquid.
So for aluminium, you're passing electricity through molten aluminium oxide.
Essentially, yes, though it's dissolved in cryolite to lower the melting point, but the principle holds. The electrical energy forces the aluminium ions to accept electrons and become neutral aluminium metal atoms. It's a brute force method.
And incredibly energy intensive, you said.
One of the most energy-intensive industrial processes we have,
Yeah.
because you're literally fighting against the fundamental chemical nature of these highly reactive elements.
Okay, what about the metals in the middle of the series? Like zinc, iron, lead. They're less reactive.
Right. For these medium reactivity metals, it's easier. We usually first convert their ores, often sulfides or carbonates, into oxides. Then we can use carbon, typically in the form of coke, as a reducing agent.
So you heat the metal oxide with carbon.
Yes. Carbon is just reactive enough to steal the oxygen away from these middle-tier metals, leaving the pure metal behind. It's a standard smelting process, much less energy-intensive than electrolysis.
And finally, the ones at the very bottom, the least reactive, like mercury, copper, maybe silver and gold.
Their chemical indifference makes them the easiest to liberate. Often you just need to heat their ore, sometimes just in air.
Like cinnabar, which is mercury sulfide.
Exactly. You just heat cinnabar in air, the sulfur combines with oxygen, and you're left with liquid mercury metal. No complex chemistry, no massive electricity needed. Their lack of reactivity works in our favor during extraction.
Okay, so we extract them, but then we have to protect them, right? Because many metals corrode.
That's the downside of reactivity. Corrosion is basically the universe trying to return the metal to its more stable, lower energy state, usually an oxide or sulfide.
We see it everywhere. Iron rusting, turning brown and flaky. That needs both air and water, right?
Both are essential for rust. Then you have silver tarnishing, getting that black coating, which is silver sulfide, and copper developing that characteristic green layer, which is basic copper carbonate.
But then there's this amazing story, the iron pillar near the Qutb Minar in Delhi.
Ah, yes, a true marvel of ancient engineering. This huge pillar weighs about 6 tons, built over 1,600 years ago.
And it's just standing there, barely rusted, despite centuries of Delhi weather.
Remarkably resistant to rust. And the incredible insight isn't that it was perfectly coated or anything. The secret is in the iron itself.
What did the ancient Indian metallurgists do?
Analysis shows the iron has an unusually high phosphorus content, likely from the specific ores and processing methods they used.
And the phosphorus helps.
It seems so. This high phosphorus content allowed a very thin, dense, protective layer of a compound called crystalline iron hydrogen phosphate hydrate to form on the surface over time.
Like a natural protective coating created by the metal itself.
Exactly. A passive film that adheres strongly and prevents further moisture and air from reaching the iron underneath, effectively stopping the rusting process cold. It's incredible foresight or perhaps skillful practice developed over generations.
Wow. Today, we have other methods like galvanizing, coating iron with zinc.
Right. Zinc is more reactive than iron, so if the coating gets scratched, the zinc corrodes preferentially, it sacrifices itself, protecting the iron underneath. Painting and oiling also work by creating a physical barrier.
But maybe the best approach is changing the metal itself through alloying.
Absolutely. Alloys are homogeneous mixtures of metals or metals with nonmetals designed to improve properties. Pure iron, for example, is actually quite soft and rusts easily.
But add a tiny bit of carbon.
And you get steel, which is much harder and stronger. Add other metals like nickel and chromium to the steel.
And you get stainless steel, which fundamentally resists rust and corrosion.
Exactly. You engineer the chemical properties you need. Another great example is solder.
Used for joining electrical components.
Right. It's an alloy, usually of lead and tin. The key property, it has a very low melting point compared to the metals being joined.
Which makes it perfect for melting easily onto wires or circuit boards without damaging them.
Precisely. Alloying lets us fine-tune metallic properties for specific human needs. Hashtag tag tag outro me now.
So we started just by looking at a shiny metal pan versus a dull piece of rubber, and we've ended up on quite a journey.
We really have. From just observing physical properties like shine and hardness through these really quite violent chemical reactions.
Fire on water.
Fire and water, yeah. And then all the way down to the hidden atomic architecture, the way electrons are exchanged to form bonds.
It really shows that classifying elements is this multi-layered process. Observation, reaction, and finally understanding that atomic structure.
And we've seen the extremes, the most chemically frantic metals like sodium, which have to be basically locked away in oil to stop them from self-destructing.
Right. Compared to the least reactive, like gold, which are so chemically indifferent, so stable, they're actually found just lying around in the earth in their pure free state.
That chemical inertness is remarkable.
So that contrast brings us to a final thought, something for you, our listeners, to maybe chew on. Gold. It has symbolized enduring value, wealth, power across pretty much every human civilization, hasn't it?
Undeniably, the metal of kings, of treasure.
It's so unreactive, it just ignores water, ignores oxygen. It takes that specially engineered, violent royal water, aqua regia, to even dissolve it. Now, think about the extreme energy-guzzling effort, that electrolytic reduction we have to go through just to extract common, useful, but highly reactive metals, like aluminium, from their natural ore state.
Right, fighting their nature.
So considering that intense effort needed for common metals, what does gold's sheer chemical stubbornness, its profound indifference to reacting, tell us about why humanity, deep down, ultimately decided that was the most precious material? Is it simply because it's the one element that just refuses to change, that endures chemically?
A fascinating link between fundamental chemistry and what we value as a civilization. Something to definitely think about.
Indeed. Well, that's all the time we have for this deep dive into the secret lives of metals and nonmetals.